Hello and welcome to the rate and extent of chemical change. So these are GCSE exam questions. So the animation in the background there. So this is about chemical changes, and these questions have been taken from real exams, so real GCSE exams, and different exams. So obviously the numbers might not always line up, might go in order because they're from different exams. Okay, so let's have a look at this one. This is similar to a question we saw before, but a bit different in another video. Iron rusts when it is left in certain conditions. Figure 9 shows the apparatus used to investigate the rusting of some iron nails. So we've got A, air and water. B, air, there's no water, there's drying agent, so there's no water. And C, oil and boiled water. Explain why the iron nail in tube A would rust, but the iron nails in tube B and C would not rust. It's quite a subtle question. Okay, so let's explain this. So iron needs both oxygen from the air and water to rust. Iron nail A has both oxygen and water. Iron nail B has only air, so oxygen, and no water. And iron nail C has water, but the oil will stop air being in contact with the iron nail. Okay. Magnesium is more reactive than iron. Figure 10 shows an iron nail with a strip of magnesium wrapped around it, placed in some water. The tube was left for a few days. State what would happen to this iron nail. So magnesium is more reactive. So magnesium would act as a sacrificial metal. Would act as a sacrificial and would corrode, but the iron nail would not rust. Okay, when iron rusts, a brown solid forms on the surface of the iron. What happens to the iron as the rust forms? Iron is hydrated, the iron is neutralized, the iron is oxidized, or the iron is reduced. So it's gained oxygen, so the iron is oxidized. Figure 11 shows the apparatus that can be used to electrolyze sodium sulfate solution using inert electrodes. Inert means it doesn't react with the solution. Hydrogen is produced at the negative electrode during electrolysis. Describe the test to show the gas is hydrogen. So this is the standard hydrogen test. So place a lit splint into a tube of hydrogen. And a squeaky pop sound will be heard if hydrogen is present. Okay, standard test for hydrogen. The word equation for the reaction between copper carbonate and dilute sulfuric acid is copper carbonate plus sulfuric acid goes to copper sulfate plus carbon dioxide plus water. Complete the balanced equation for this reaction. So the formula for hydrochloric acid, sorry, sulfuric acid is H2SO4, and we've got copper sulfate, so CuSO4. Okay, here you've got copper carbonate then. So let's have a look, balancing it. So we've got one copper, 3 oxygens on, so 3 plus, that's 7. So we've got 4, so 6, 7. Okay, oxygen's okay. Hydrogen 2. So actually it's done, it's already balanced. Calculate the relative formula mass of copper carbonate CuCO3. So this is easier than it looks as well. We cover the atomic masses. So Cu, so we've got 1 copper, 12, plus 1 carbon. Oh, that's not the wrong, I did it in a strange order there. So 1 copper, Cu, 63.5, plus 1 carbon, 12, plus 3 oxygen, so 16 times 3. It's just a maths question, really. So we get the calculator out. So 63.5 plus 12 plus, and you have to put that 16 times 3 in a bracket. 123.5. So it's nothing too difficult there to work out. What is a chemical test to show that a gas is carbon dioxide? So pH of the gas, pH is 4. No, because that would be acidic gas. That could be chlorine. Put a lighted splint is extinguished. Could be. Okay. Put a damp blue litmus paper. No, that's chlorine again, because it's acidic. Bubble the gas through lime water. Lime water turns cloudy. So that one is a test for carbon dioxide. Figure 12 shows a conical flask containing dilute sulfuric acid. Copper carbonate is added to the acid in the flask. The copper carbonate is added 1 spatula measure at a time until the reaction is finished. So we've got sulfuric acid and copper carbonate. So copper carbonate is green. So state 2 observations that would show the reaction is finished. Okay, so that the reaction is finished few ways. So the copper carbonate will not dissolve anymore. So any bubbling, so effervescence, will stop being produced. Yeah, sometimes it's called being in excess, doing that. Describe how you would obtain a solution of copper sulfate from the mixture and how you would obtain pure, dry copper sulfate crystals from the solution. Your description should include the apparatus you would use. You may wish to use diagrams. Okay, so copper sulfate from the mixture. So we've got copper carbonate and dilute sulfuric acid. So we kind of go from where we started off. So add copper carbonate to the sulfuric acid. Until reaction is stopped. That's been called in excess. Okay, so what you do then, so you use a funnel and filter paper to filter excess copper carbonate so it's a make draw, so I'm going to give a little symbol here. So it's a funnel, so filter paper, beaker. So you put it in a conical, wasn't it? So okay, so you put the solution into there and it will drip through. Okay. So it has to get the solids off. Excess solid copper carbonate. So there's two things you do after this. So use a Bunsen burner to heat the mixture over a flame until the word excess water has boiled away. Okay, so number 4. So the water, still some water might be there. Place the mixture, so it might still be a little water. So it might look like a powder by now, into an evaporating basin. And leave on windowsill or in an oven, like a chemical oven, not a kitchen one, chemical oven, to form crystals. Okay. Calcium carbonate reacts with hydrochloric acid to produce carbon dioxide gas. The rate of reaction between calcium carbonate and dilute hydrochloric acid at room temperature was investigated. The investigation was carried out with different sized calcium carbonate pieces. The mass of calcium carbonate and other conditions were kept the same. The results are shown in figure 15. The size of carbonate pieces used, large, small, and a powder, so it ground up. Calcium carbonate chalk, so you can grind it up. So volume of gas produced, 1648, 90, so it's going up. State using the information in figure 15, the effect of surface area of the calcium carbonate on the rate of this reaction. So powder has a bigger surface area. So powder has the largest surface area. Okay, so the greater the surface area, the faster the rate of reaction. Okay, 1 mark. The calcium carbonate powder produced 90 centimeters cubed of carbon dioxide in 5 minutes. Calculate the average rate of reaction in centimeters cubed per second. So it's actually not as hard as it looks. So 5 minutes. But we need it in seconds. So 5 minutes. So 5 times 60. Okay, 5 times 60 to give us how many seconds are in 5 minutes? It's 300 seconds. So 90 centimeters cubed. So we need, so rate is always something over time. So in this case, the rate is 90 centimeters cubed over 300. Okay, so we've got to do on our calculators 90 divided by 300. So 0.3. So it's 0.3 centimeters cubed per second. Seems like a low number, but it's per second, not per minute. Okay. The experiments were repeated at a higher temperature. The rate of reaction of each experiment increased. Explain in terms of particles why the rate of reaction increased when the temperature was increased. Okay, so increasing the temperature caused the particles to gain energy and move more quickly. Faster would be a way of saying that. Move more quickly. So this would increase the number of collisions for reactions the particles also hit each other with greater force. Force and enough energy to react. Increasing the rate of successful collisions. So these are very common questions, okay? These are very common questions about the temperature and about the surface area in these reactions. So yeah, so look over that if you need to, and good luck in your exams, and hope to see you in another video. Thank you. Goodbye.